'Cause he was burling down and down white water, 'cause that's where the log driver learned to step lightly. Oh, hey there. Let's take a look at a capacitor example here. This is going to be like an intro capacitor, so a pretty standard one. We have a 0.2 meter by 0.3 meter parallel plate capacitor with a separation, a D, of 1 times 10 to the minus 3 meters, and it's through an air gap. Okay, so pretty standard capacitor here. What we're asked initially is, what is the capacitance of this thing? And remember, capacitance is based off of the geometrical properties of our capacitor. So a capacitance is based off of the dielectric we have times epsilon naught times the cross-sectional area divided by that distance in between the plates themselves for a parallel plate capacitor. In our case, we are through an air gap, so we have a kappa value of 1, so we could kind of ignore that. That means all we need here is epsilon naught, the cross-sectional area, as given by our width, length, and width of our plate, and then d, the separation distance. So this isn't too bad. In a prior video, we talked about epsilon naught in passing. I didn't give you a value for that. Here's the value now. The value for epsilon naught is 8.85 times 10 to the minus 12. And it's got some pretty strange units. The units are coulomb squared over Newton meters squared. So kind of a weird unit, but they work out so we get coulombs in the end. The cross-sectional area here is the length multiplied by the width of the overlapping plates. So that's going to be 0.2 meters times 0.3 meters. That gives us a meter to get rid of the meter squared, which is very nice for us. And then we just need to divide this by the gap distance here, which is 1 times 10 to the minus 3 meters. So 1 times 10 to the minus 3 meters. And if we throw all these numbers together here, we're going to get something very small, actually. We're going to get something that is about 531 picofarads. Remember, farads are the unit of capacitance. Pico is times 10 to the minus 12. So a very, very small amount of capacitance here. So let's look at the next problem here. In part 2, we have a 12-volt battery applied to the parallel plates. So we'll see this kind of in circuits later, but here are our plates, and we hook up a 12-volt battery to them, and it charges this thing up. Positive, positive, and then here's our negative, negative. What we're looking for here is what's the charge on this capacitor, and we're going to say the capacitor is fully charged after a long time. So we're looking for charge. We're looking for Q, and Q on a capacitor is just equal to C multiplied by V. We already know the capacitance of our capacitor. It is a geometric property. It is some value. So this is just going to be the 531 picofarads, so times 10 to the minus 12 farads, multiplied by 12. And that gives us some number here. What number is that? It's like times 10 to the minus 11, maybe times 10 to the negative 10th. I don't know. This is a number. I don't want to find it right now. What matters is the setup. The rest of it is calculator. And calculators are the worst. Always gives me pain. What's the electric field between the plates equal to? So we're looking for an E field here. What's the electric field between the plates? Well, this is a little weird. But this actually isn't very difficult to solve at all. Let's think about potential, right? We know an electric field multiplied by some separation or separation distance on the things creating the electric field is equal to a voltage. And this is where things are a little different, because while we're normally talking about R for any three-dimensional space on the parallel plate, this is just the letter D here. So what we have is the electric field is just the voltage divided by the gap. So we're just going to get 12 volts over 1 times 10 to the minus 3 meters. And when we run that, we get, what is that? That's like 1.2 and then -3. We should get like 1.2 times 10 to the minus, or times 10 to the positive 4th. And that's units of newtons per coulomb for an electric field. And last but not least, it's kind of a strange question here. What area would be needed to give a capacitance of 1 farad, so 1F, if the separation between the plates was still just 1 times 10 to the minus 3. So we're getting rid of the 0.2 and the 0.3 meters, and we're saying, look, let's just build this capacitor as big as possible. Our customer wants one that is 1 whole farad in capacitance. So what would we need to build for that? Well, if we take our capacitor equation and we rearrange it a little bit, we'll find that the area is equal to the capacitance multiplied by that gap divided by kappa, which for an air gap is 1, and then epsilon naught. So if I want this to be 1 farad, and I know the distance is 1 times 10 to the minus 3, and I know epsilon naught is 8 times, well, 8.85. Let's put the full thing in there. 8.85 times 10 to the minus 12. Oh boy, I've got a minus 12 in the denominator. When that comes up top, this is going to be a huge number. We're actually going to see this is approximately, because I don't feel like solving everything out, this is going to be approximately some number, and probably something on the order of times 10 to the 9th, probably closer to times 10 to the 8th meters though. And this right here, that's the size of a city. That's like Dallas. Wait, if you just want a 1 farad capacitor, you need to build it as large as a city? That seems insane. Because I have 1 farad capacitors in the back of our classroom. So they must be doing something in order to get this size down a little bit. One of the things they could be doing is installing that dielectric, putting some substance in between the parallel plates. The other thing they could do is they could geometrically create the capacitor in a very clever way. We've been talking about parallel plates as just here's a plate, and that's it. And I'd have to have a very, very large spread out plate. What we'll actually see on commercial capacitors is they will take large plates, and if we kind of look at it from the top like this, what they'll do is they will fold them over onto each other repeatedly, like you're folding a piece of paper into a fan. And then once they have this like very long skinny thing like this, then they'll roll it up kind of like a fruit by the foot, and then they'll pack that into a cylinder. So they'll have this kind of cylindrical shape that actually still has all of the cross-sectional area. They just bundled it up very tightly. The other thing that they'll do is, instead of making these traditional parallel plate capacitors, there are other capacitors out there that exist known as ceramic disc capacitors. Those ones don't really follow this equation. They're kind of based on the properties of the ceramic itself. But yeah, we can use a lot of cool geometric ways to kind of pack more area into a tighter spot. You just have to unfold it and unroll it in order to get to it. Okay, so this was a kind of simple example of just what we're thinking about for capacitors here, some of the stuff we may have to do with them. We'll see in our next 2 videos a little bit more complicated videos as we get further into them. Okay, until next time though, this is finished. Adios, take it easy.